Okay, good morning everyone. Today again we are talking about quantum mechanics, and today of course I'm going to talk about it. Yesterday you have talked about quantum mechanics with Georgia, but today I will first give you some information about hybrid machine learning. Then I will introduce you some nice concepts in a paper. It's a recently published paper in Nature Communications, so I'm sure it will just attract your attention. So let's first talk about what is hybrid machine learning. So what comes to your mind when I say hybrid machine learning? Any idea? What is hybrid? Just forget machine learning, but just think about hybrid. What is hybrid? Two or more different things come together, yes. In machine learning, we use different concepts, complementary methods. So when we use them, they are beneficial in building some models. So we choose not just by applying one method, but we apply more than one method in some cases. For example, in neural network architecture, we build autoencoders, and in your autoencoders, sometimes you use continuous data. And in continuous data, you have to do some dimension reduction. So what can you do to reduce your dimension? You can do PCA, right? Or in transcriptomic data, you can just select some specific genes, differentially expressed genes. But if you are interested in binary data, you don't want to reduce any dimension, you can use all of the features. Right? So, or another example, you can use CNN in your architecture, and you want to use a transfer learning approach, and with your data set, you can use the main data set as your source data set, and you can do feature extraction. And after feature extraction, you can do another machine learning approach, and another machine learning approach can follow it. So you can use many different approaches. And in many cases, actually, hybrid methods are better than just traditional, like I applied and found some predictions type of approach. So usually, we don't just apply one method, we apply with some other methods. So now I will say more broadly that we use physics-based concepts, chemistry-based concepts, like we use constraints. In physics-based concepts, we can use force fields in molecular dynamic applications, right? You know some force fields, Amber, charm. Yeah? So we can apply this, and with the results, we can apply machine learning. And in chemistry-based constraints, we can use some drug structure info, like smiles, you can filter some features, then you apply machine learning. It's also hybrid. Okay, it's in a concept, you understand what I say, right? Okay, so I will show you first aquaculture example, which one I showed early in the second lecture of my talk, and let's solve it here. This is the hybrid approach. In the first step, they just want to predict dissolved oxygen. But in order to predict it, they first do some quality controls, like they find some missing values, outliers, and they perform normalization. And after this step, they use this time series data and perform prediction. In the first step, they perform convolutional neural network. This is the process they apply. They use several activation functions, phase normalization. They apply convolutional neural network for feature extraction. Okay, this is the first step of the hybrid approach. Then they use self-attention, which ChatGPT uses self-attention for averaging the weight or finding the weight. Then they apply another neural network, bidirectional simple recurrence unit. It uses the time series data. Information flow first comes from early layer to the last layer, then last layer to the early layer. That's the reason why we call this pi. So they integrate three different machine learning approaches, and it's called as hybrid. And in the paper, this hybrid approach is the best performing one. When they apply just CNN or bidirectional single recurrence unit, the performance is not as competitive as this one. Okay, so not always, but mostly, hybrid approaches perform better than other approaches. And this is my paper with Dr. Professor Cesarma. And in our approach, we use actually a hybrid approach. Maybe you will understand this example better. We used cell line data, and our data were gene expression, somatic mutation, and copy number data, and we also had drug response data. So before combining all of the data, we first intersected our genes, then we found some differentially expressed genes. So this is a constraint. Our first constraint was to find these differentially expressed genes. So instead of using thousands of genes, we just filtered our gene counts, the most informative ones, with this step. This is a constraint. Okay. Another constraint was that we used drugs with same pathways. So mitotic inhibitors, cytoskeleton inhibitors, DNA replication inhibitors, EGFR signaling inhibitors. We combined specific classes of inhibitors. That was another constraint. So we used different autoencoders. Here the data was continuous, and in other omic datasets it was binary. So with this step, in continuous especially, we reduced the dimension, and we found some important features. Of course, we found also here, but it was most effective, especially in continuous state. Then we integrated specifically for expression mutation combination, integration, expression mutation copy number integration, and expression copy number integration. This is also a hybrid approach, and we performed the best with the predictions of the papers which apply the same datasets. Okay, this is the paper I want to show you. It has been published recently, and it's a quantum machine learning based refinement algorithm for proteins, just for proteins. It's a nice paper, and I'm sure you will like it. So, what's the problem? You know AlphaFold? In AlphaFold, we can predict protein structures for stable proteins, but when we are interested in IBPs, as Orthodoja did do, we have some problems. We cannot predict in three-dimensional structures, so we have to do something with the AlphaFold approach. We can use physics-based constraints, chemistry-based constraints, so that our predictions may be better than AlphaFold predictions. So, in these cases, you can apply some equations, differential equations, some constraints. In the paper, they just want to show that with the classical restraints approach, how do they find the results, and with the quantum-based, chemical-based refinement approach, how their predictions improve. So the problem is that the structural refinement mostly rely on library-based stereochemical restraints. So here I would like to ask you, what is stereochemical restraints? Maybe you know from your chemistry classes or the lecture which was Georgia held yesterday. Maybe you will remember. Stereochemical restraints.
But it's stereochemistry. Polarization of surface that makes the bonding proteins is facilitated.
Just in simple atoms. Like bond length, bond angle, pi psi angle, diagonal angles, this kind of metrics are stereochemical restraints. Okay. And with the known chemistry, with these approaches, they just use covalent interactions, but these approaches miss non-covalent interactions. What are some non-covalent interactions? Yes. Any others? Yes. So, especially in the side chains or rotamers, there are some interactions, non-covalent interactions, salt bridges, maybe you will remember. So, these type of methods just miss this kind of interactions. So, how quantum mechanical requirements apply in this case? It may significantly improve the prediction results, but its cost is huge. I mean here, the computational cost is huge with large biomolecules. And for this purpose, they developed this Aqua. Here, Aqua is totally irrelevant to BioAqua. AI-based quantum refinement tool. So here, they just developed a method that it reduces the complexity of ON square or ON cubic size to ON. So its computational time significantly decreases and it can be used. Otherwise, it's just computationally more complex. It will be computationally more complex. So how do they do that? They use a neural network architecture, and it's called as AI-MNet2. And using this approach, they perform quantum refinements. And it's called as machine learned interactive potential. So what could it be, like interactivity? This study is for proteins, large proteins, and it's not so possible to perform this approach normally for large proteins, but they do something special so that they can perform this refinement. And the procedure is machine learned interactive potential. Just in simple.
Does it learn the interaction between proteins?
Yes. And the approach is known as divide and conquer. It's a popular approach in programming. Instead of solving the question once, you just divide the problem into several sets and you do each step separately, so it will be much easier. It's simple here. They just divide the proteins into several parts. Then they use their method, and it is less complex. And of course, it makes this cost much lower. So they refined 41 cryo-EM and 30 X-ray structures. And they predicted better geometry and equal improved experimental fit. This is important because if you use some new methods and you don't find a better geometry or you predict poor, that would be nonsense. Why would you use quantum refinement? But here, they can do that. And the other important thing, they can accurately identify protons. And they show it with the Parkinson disease-related homoprotein DJ1 and its factorial homologue YAGL. Okay, I will show these results. But before that, why this protein location is important? Any idea?
Maybe location adaptations, structure and function of
Like, think about hydrogen bonds. Some side chains can make hydrogen bonds, and you should show they could effectively do these hydrogen bonds, and it can be done with protonation. With the simulation, you have to show it the hydrogen bond position and where can the hydrogen bond located and what is the distance of hydrogen. So with this approach, they identified both for the protein and its homologue. And you will see that in the results, they will find effectively with this tool, quantum refining tool, but it will not be possible with other classical tools. And what's the impact? Combine AI speed with quantum mechanical precision and open the next generation strategy for future refinement. So what is the limitations of library-based restraints? So its restricted scope is it can only include covalent terms like bond lengths, angles, torsions, gravity, and it doesn't include non-covalent bonds, low resolution weakness. Like there are important restraints like these pi and psi angles, and chi angles in the side chains, hydrogen bonds. And do you know this stacking energy, pi stacking? These methods doesn't consider these kind of bindings. This pi stacking is the bonding used in benzene. You remember? Yes. That's the pi stacking. And these are important for secondary structure, and it's manual dependence. So you have to manually find some high resolution homologs. Why? Because you will find the homolog, and with the homolog you will compare, and it's a slow process. It takes time. And limited chemical coverage. Only non-residues and ligands can be used with the approach, but if you use some other ligands or crosslinks, you have to do some parameterization steps, and it may result in failures and overcorrection of quality deviations. In this case, normally these are the local interactions, but these restraints can make you feel that, okay, these are just errors and we have to correct it, but actually the approach is totally wrong. So correct terms can be incorrectly changed. So what are the simple restraints to quantum refinement? Simple restraints, very low computational cost, and maintain basic covalent geometry only. And it can use classical force fields and physical realism, but not the parameterization of the molecules. Cannot distinguish equivalent bonds in different environments. And quantum refinement integrates experimental data fitting and quantum energy minimization, benefit entire model. Not so important. Technological advances. Yeah. So GPU acceleration point is important. I will show you a few moments later, and you will see that how GPU affected this process. Normally, in the early of 2010s, without GPU, it was slow, and it was actually impossible to just refinements for even small proteins, but now it's totally possible. And fragmentation methods, scalable quantum mechanics for large system, especially interaction-based model partitioning into chemically meaningful fragments, is computationally demanding. Here, the one I said here, interaction-based model partitioning into chemically meaningful fragment. This is the approach. It can be used like divide and conquer approach. You just individually use the sum parts and use their parts for refinements. But here, they will go even further. They will no need for this approach, but directly will perform for a large protein. So in 2010, it was impossible for performing quantum calculation, and it could be done only with some small molecules. But in 2012, GPU helped acceleration of quantum mechanics, applications in protein sequences, especially for refinement, but it was limited to peptides and very small proteins, hundreds of atoms. Then in 2017, the approach with quantum and with the environment, QR with fragmentation, that's the actual meaning, quantum with environment, QM-based protein refinement, slow resource intensity, no inherent size limits. So from 2012 to 2017, it improved a lot. So they regarded the quantum part with the quantum mechanics and the R part with other classical approaches. So they combined it. But now, in 2024, it has machine learning potentials. Fast revolving classical force fields, accuracy is high, no fragmentation required. So this was the fragmentation method, but now, and even in the paper, they don't need fragmentation. So it's fast and accurate. And this is the refinement tool. This is full quantum refinement and it's accurate, but computationally prohibitive. And machine learning interacting potentials provide a scalable alternative. In the approach, they use this neural network architecture. It's a bit different than the architecture you know in neural networks. And they trained a custom polypeptide dataset with implicit solvent correction. And it incorporates rotation invariant features, message passing for many body interactions. This is related to neural network and explicit total charge handling. So what are the basic results? The accuracy is high, but at a fraction of the cost. And in the refined cryo-EM and X-ray models, they show superior geometric quality, equal or better experimental data, and significance using full protein quantum refinement using an ML potential. And outperforms other multi-layer on-ion type methods in efficiency and accuracy. Now I will show the results. This is the figure I think interesting. Like they used like 25,000 atoms, and they can do this process like less than 0.2 seconds. Like when they use 100,000 of atoms, they can do it like around 0.5 seconds. And they found in the paper that the count of atoms was like 108,000, and they can do this all using approach. I mean, no divide and conquer approach. They just use all the proteins in all the atoms in the protein, and it was like 0.8 seconds or so. So it is fast. It's not like ON square or ON cubic. So it's linearly. It's complexity so linear, so it can be performed in a fast approach. So how was the performance? They use 41 cryo-EM models, 20 low resolution, 10 high resolution X-ray. So here I will ask you, why do they choose low and high resolution X-ray models?
I think it should be, one should be at atomic level representation, the other one will be the structure representation for that feature.
I don't understand what
I
you say.
mean, low resolution and high resolution.
Okay.
For high resolution, you want to go deeper.
Yes.
And for low resolution, we just need to see the things overall. So maybe for this reason.
So in high resolution, you will see not so much improvement.
Yeah.
But with low resolution, you will see improvement much more. Yes, exactly. That's a specific. That was a specific reason. And what are the evaluation metrics? They use stereochemistry and model data fit criteria. And mole probability validation for geometric quality. Have you heard this term? Mole probability. It's a metric that includes many like angles, torsions. It's a combination of score metric, and it's important in evaluating this kind of studies. And hydrogen bond cavity metrics and performance for quantum refinement time. And they identified that with the tool, the time related to perform this is 2 times slower than the conventional method, but if you add additional restraints, then it is faster than the conventional method. So they compare conventional method without restraints. They use conventional method with other additional restraints, and they use quantum mechanical application. And quantum mechanical application is in the middle in terms of speed. So computation time, around 70% of the models, it was like 20 minutes. And maximum was 1 hour. And outcome, efficient and high accuracy. So this is the workflow. You have to check model complexity, add missing atoms, resolve steric clashes. And do you know these steric clashes? In sidechains especially, you have van der Waals forces. So sometimes model think that like these van der Waals forces result in steric clashes. So it's again a metric, and it's important in geometry finding. And symmetry handling for X-ray only is too much detail. And refinement execution, they use a package for refinement, combine experimental data with this tool, and they have outcomes. Now I will go to directly figures, because these are too much detail. Yes, these are the results. Let me go one by one. The first one, the score I showed you before, mole probability score. If it is lower than 2.5, the model is doing good. If it is lower than 2, it's even better. If it is lower than 1, it is excellent. So here, they compare the quantum model, quantum mechanical model with the conventional one, the blue colored one, the conventional one. This is the quantum one. So these are the medium values. So the medium value is lower than the conventional one. So here it outperforms. Okay, with this score, with this metric. This is the Ramachandran Z-score. Do you know Ramachandran plots? What is it for?
Tell us about the amino acid structure probability.
You use it for secondary structure.
Yeah.
You find some pi psi angles, and here they use a metric Ramachandran Z-score. In statistics, we have Z-scores, and if the Z-score in the green area, it's good. But here, the conventional one, the simple same model, low, medium value, but here the medium value is higher in the green area. So again, here the quantum refined model outperforms and successful. How about this one? Which metric is it? Okay, this is another one. C alpha based low resolution annotation method. So here, this is the low area. If you are in the green range, you are doing excellent in metric. But here, even this quantum refinement tool is in the border, but the blue one is higher, so it's performing better, but not in a wanted region. You know RMSP? What's RMSP? What stands for RMSP?
Standard deviation.
Yeah, why do we use it?
I think it's also to tell us about the size deviation from the mean.
Exactly. So here, if your deviation is small, your structure is close to the original structure. So here, blue one actually is better than the quantum refinement tool, Aquaculture. But if you have an RMSD score lower than 0.5, it's excellent. So both are excellent. Okay. So how about this CC mask? This is a metric only for cryo-EM, not for Hooke's rate. So this is the correlation coefficient, and it's like not exactly the same with the correlation, Pearson correlation. Like the range is between 0 and 1. The higher value you have, the better the model is. Okay, so here the blue one has higher median than the Aquaculture. Okay, and they are higher than 0.7. It's okay. But if it were like 0.8 or higher, that would be much significant. And this is again for the cryo-EM result, not for X-ray. The lower you have, the better it is. So here, none of them can be in this range, but Aquaculture is better. And what about R3? Do you know R3? What does RES stand for?
The molecule, upper stability, how it would be, their energy.
Yes, but here R is residual. Residual. Like in machine learning, what we do cross-validation, right? Like we find some, we take some training set and we hold some validation set. R3 is the validation set in machine learning approach. So if the model has a good performance in training set and the R3 is higher, then your performance is better. Okay, so here R3 is nearly identical and blue one is a bit higher. So this is the R3, and what about that R?
Mr. Question, I'm a little bit confused about the residue. Residue represents a single atom or single molecule? Like single amino acid or
It's not single atom, single mode.
single molecule? Amino acid, like single amino acid?
It can be minus, it's just person.
No. Are free we locate are free for a single amino acid,
Yes.
not for a single atom.
We use it for single protein actually, not amino acid. We use two protein, the human one and its bacterial homolog.
Okay.
We calculate it for just for the human one. So it's like a validation set. They apply the machine learning, and if this R3 is higher, then it's performing better. And that R is the difference between the residual value you have and the calculated R3. It's called as R work minus R3. So if it is like lower, it is better because your baseline and your prediction, it must be just close. So here Aquaculture is better. And what about these plots? Have you heard kurtosis? I will go faster because of time limit. In kurtosis, normally normal limit for the y-axis is 3. If it is lower than 3, you are in the correct range. So they take the ln value, ln kurtosis. So ln3 is around 1.1. So here, these are the values for your predictions if they are mirror images or they show symmetry and the points are in this range, you are performing better. the values wouldn't be lower than 1.1 in the left side and in the right side. So is this a good result? Not because you see these points. How about this? This is the standard approach. This is the standard plus additional restraints. You see some points, but in Aquaculture, it's excellent, right? Even though you have some problem here, but when you compare it, Aquaculture is totally okay. And how about this one, RMST? With the standard approach, they use speeds, and for the Aquaculture, they use the approach. You see some red and green, red and blue dots, and this is the diagonal. If you see red dots below the diagonal, then it means that RMSD of the Aquaculture is better. And here we see some red points here and some blue here. So we cannot exactly say which one is doing better. And this is the overall metric for the all I told you, but the results were in terms of median here, and they use mean here. So as you see, this star, red star is for Aquaculture, and here they compare it with the conventional state and additional approach with this sign, and they show their performance comparison. Okay. This is another image for the results. What do you think about the results? What's your opinion? What does it show? Comparison of low resolution refined models with high resolution homologs. So they compare their predictions with the homologs. Homologs are your ground truths, your real wanted values. Okay, so it's in green. If you see blue or orange near the green line, you are doing better. Okay, so which one do you think is similar to the behavior of green line? Blue or
Orange.
Orange. Yeah. Orange is Aquaculture. Blue is the standard constraint model. How about this?
Again,
Also, very low.
Okay. How about this? Here. In all cases, orange is performing best Aquaculture. So, next question. What is E68? What? What's the name of E? Glutamic acid. Glutamic acid at residue 68. They especially show some residues because they are important in structural terms. Okay, so they show it can Aquaculture is better at identifying especially this residue. How about this? E36. It's again glutamic acid at residue 36. And why?
virus.
Tyrosine, yes. And F, phenylalanine, they have a ring structure like phenylalanine, tyrosine, and it is easy to convert these amino acids, phenylalanine, tyrosine, phenylalanine, and tryptophan is a bit similar to this ring structure, but not here. How about H? Yes, histidine, and the final one,
Iron.
what?
Iron.
Threonine. Threonine. So these are specific points, and they are actually structurally important. So they compared these methods, like they use force fields Amber, Rosetta, desampling-based methods, Red Mark 5. This is another refinement. So for Cranium tools, they used several paths, and it's mostly used for Cranium refinement tool. And in the results, I will directly show the figures. These are just text. So this is R3, I told you. If R3 is higher than you are performing good. So this is the frequency. So how many times you predict the highest R3? 0.33. Here, the red is for aqua red. Others are the other methods. So just focus on the red color. So do you think aqua red is doing better here? These are the frequency. 0.27 is like 50 times you see in the example. And it's mostly with aqua. Okay. Here they are equal. Aqua is okay. The best one. Lowest one. It's okay, but not the best one. Okay. So how about this? R3 plus minus R1. The lower it is, the better the model makes predictions. Do you think Aquarium is performing better? As you see, you don't even see here the red color. You don't see the red color. It's low, it's high here. So the low values is good for Aquarium, right? You see 0.05, 0.02 for most of the Aquarium. So it's performing the best with this method. And how about correlation coefficient? The higher it is, the better it is. Do you think Aquarium is performing the best? And they are comparing only the SE metric. What is SE? Several, because it's crowded EM results. CC mask is only used for crowded EM. So, do you think Aquarium is performing better than the other one?
In some groups.
This is the best metric, but you see it is not performing well against SE. And here again, so it's not the best crowded EM result. Normally, you expect red bar is longer than the green one, but the other one is performing better. EM Ringer score, it's similar, right? You see bars are similar. The lower it is, the better it is. So it's performing similar. Ramachandran Z score, if the Z score is the absolute value is lower than 2, it's the best. Okay. If it is around 2 and 3, it's okay, but if it is greater than 3, it is performing worse. So, which one do you see most here? The yellow and red one. What is the yellow? Rosetta. Oh. Okay. They are competing, but Rosetta Hole is much better. How about this plus, this 3 plus? The lower it is, the better the prediction is. So you see here, Aquarium and Rosetta lowest. Here again, lowest. In IMSD, lowest. So they are again competitive. How about this kurtosis plot? Which one is better? We don't have the Aquarium here. I always showed it. Of course, Rosetta. We don't see these black dots. Okay, you see here, but you don't see, and values lower than 1.1, 1.1. Points are all located in this plot. So Rosetta is actually performing much better than others. So in the case study, they will now show you results for these two proteins. You can just read these parts, but I want to show you the result part. This is the protonation part. They want to show how they can predict protonation with this refinement tool. This is the experimental data. Okay, they just use the PDB file, and this is the experimental. This is your ground truth. You want to predict this matrix, is the distance Armstrong. You should find similar distances. Okay, this is for Aquarius start point. It's normally 2.49, but in the approach they divide it especially in half, so they just think it's 2.5 and divide this as 1.25, 1.25. This is just for an initial step. Okay, and of course they again do same thing here. They equalize the values, and this is the ideal value for restraint model. Okay, these are the ideal values. They put it, and they want to see whether they can explicitly put the hydrogen there. So these are our results. Okay, so unrestrained. Do you see hydrogen here? You don't see because when you put it, you cannot exactly get great values for here. Why? Just think about it. 1.19. 1.32, not for this one. Should compare with this one. They are not so similar, right? So even with this, actually they are okay, but these are not okay. This is CO binding. So when they put hydrogen here, the results are not so good. So they cannot explicitly put hydrogen here. It's unsuccessful. How about this Phoenix refined? This is the refined one. These are the values in parentheses refined. Do you see some good results when compared it with the ideal? Right, 1.33, 1.26. It's not okay, but here it's okay. How about this? These are okay, but you cannot put it here because the refined value is not close to 1.33, so you cannot put hydrogen here. How about Aquarium? Compare results. Like even with this one and with the ground truth. Similar, right? So this oxygen part is important. So hydrogen bonding can be here, protonation can be here. These refined values are perfectly okay, so you can put explicit hydrogen here. So Aquarium can do it, but other methods cannot do it successfully. How about this result? What is this thing strange? Epsilon, delta. So what does they show? Oxygen. Okay, these are oxygen. But 2 is second, okay, but what about this? O2. Alpha first, beta second. Gamma, delta, epsilon. It's the fifth. Okay, fifth position. Fourth position. So fifth position of something, fourth position of something. And here we have the residue. What is the aspartic acid? At residue 24. Glutamic acid 15. So these are the residues, and you see the interaction between these residues. Okay. And the fifth position, fourth position. Okay, these are the Greek symbols used for the purpose. And you see a curve, and we call them as the well, two well structure. And you see some increase here. what do you think about the result? And here, again, you have the same residues, but you have only one well. Here, totally different curve, and it's also one well. So, what do you think about the results? These are for the human. This plot is for the human. This two plot is for the human, the bacterial homolog. This protein, YAGL. The first thing you should take into account that you only see black line, but you see here some black line and dashed line. And here again. So here you see two hydrogen bonds. Okay. So two alternatives. But in the bacterial homolog, you have the same values, right? The lowest one. Again, you have the lowest value, but your hydrogen bonding distance might be somewhere here, but here you have a longer hydrogen bond. Okay, because of the distance. And here you have a lower barrier for hydrogen, and it means that protonation can be both here or here. So it can be shaped. If you see this dual structure and this the amount required for this climbing bump is low, then it means it can be delocalized and it can be shaped. Proton can be shaped either here or either here. Okay, but here you only see only one value, so they can proton cannot be shared. That's the output of this figure. And how about this one? Any question?
I have a question. Can you go back?
Okay. Okay, now we can discuss.
Can we discuss the flexibility of this protein based on these results?
No. It's just for protonation. It's not about flexibility. Like
I thought that when the bond distance increases and decreases, the residue will closer to each other or go further than each other.
it will just show you between this distance, proton
Hydrogen bonding.
in the range of this, you will see protonation, but it will not be shared. And here, only at the specific level, you will see protonation, and with the two hydrogen bonding, it is the same. But here, it can change. Either with this Armstrong value or this value. It can be shared, either be here or be here.
So this is about
Yes.
okay.
These are examples just for protonation. Because it is important in requirements. And this figure, this is the density map. And what you see, this is the human protein, and again, these two figures for bacterial homolog. You see a curve, again, the residues are same. You see a peak, okay, around 4.2, right? But you see two curves. It shows two chains, A and B chains. Okay. Blue is for A, red is for B, and they have different peaks. Here, even the peaks are much different in different residues. Okay. So when you just consider the hydrogen bond here and here, with different residues, you see different peaks. Okay, this is the showing figure for density map. And you can think about that hydrogen bonding is a bit likely to happen in this part for this flood, but you cannot say it like for here, but only one hydrogen bond is possible, and only one possibility if the other figure has two possible two chains, and I think this is the final figure. You are now familiar with it. What can you tell me about it? This is the ground truth experimental result. B is for unrestrained, C is for freeze refined, and D is aquatic. But here, don't forget, we look for the equally homolog. So you have two chains, A and B chains. So you will have two different distance results. So the better you are close to these values with the experimental one, we are predicting much better. So let's first talk about understanding. Is it performing good?
Distance are okay, but it doesn't show the growth.
Yes. The key here, it doesn't show protons here. It doesn't put explicitly there. But it's not performing good. And how, which residues it here is used? Again, glutamic acid 14 and aspartic acid 23. How about mixed refinement? You again don't see hydrogen here. And how about the predictions of these distances? For instance, 1.3, 1.26, 1.25, 1.22. These are similar. And how about aquatic? Compare the values, and you will see these values much better fit to this branch root. And you see hydrogens both here and here. Carbon, oxygen, and this oxygen can make two hydrogen bonds, and you can explicitly put proton here. Why? Because I told you chain A, and the values are close to branch roots. Right? This 1.28, 1.28, 1.23, 1.23. Only the aquatic can predict these distance values powerfully. Okay. So I also have some discussion part, but I will not just talk about it. You can just read them. So I think it's the end of my presentation. If you ask anything, I can answer it. Thank you for listening. Var mı soru arkadaşlar? Okay, guys.
Seriously, for your the thing is, I was like asking myself, saying that why they are not using their function arguments so that they can know all the things, and I was searching for that, and I was like expecting this presentation about to talk about it, and present this presentation. Thank you very much. So my question is like in quantum requirement, what we are doing is in locate position of the hydrogen so that we can get all the parameters that we need. So what about how aquarium improves the hydrogen oxygen bond distance? So that is the challenging one. So is there any they are using so that we will fix that problem?
Yeah. Great question. In simple restraint and restraint plus additive models, you cannot explicitly put hydrogen bonds because the predictions are good for covalent bonds, but you cannot make good predictions for non-covalent bonds. So that's one reason why we use Aquaculture. And the second is the fastness of the quantum mechanical approach. These unstrained models are not so fast if the atomic count of the protein is larger than even 200,000. So quantum requirement is much better in that case. And as you see with these results, the performance of refinement of a quantum mechanical approach is much better than other approaches, classical restraint approaches. So that's the reason why we should use quantum-based approaches. Is it answering your question?
I think they are using the equipment so that the distance will be near to 1 Armstrong. That's the case for that in Aquarium. Because exactly you cannot find that same challenge.
Which figure are you talking about?
The oxygen hydrogen.
Let's go back to that figure. There is another figure I will just show you. I just forget it. This figure or this figure?
Maybe this figure is
Okay.
no.
Before? Okay. What makes you confused here?
So there is, like, for example, oxygen hydrogen, which is, like, for example, let's say in the B, it's 1.25 Armstrong.
Okay.
So that's the accuracy they are using. Is it right?
They just regard this 2.49 value as 2.5 because it's close. They just divide it into half. Okay, that's a random value because it's an initial start. So they will refine it. So when they refine it, they actually find 1.03. This is not the actual real value. Okay, that's the point you confuse. Yeah. Okay, so the last figure I forgot, and it's important. Then I will finish it. Yes, this is our final figure. This is the initial state and the predicted state. What do you see in all of the four figures? It acquire. Now, what is different? And you can see with arrows actually. Like here, you see only here, but it changes in this direction, right? And from what? From threonine 41 residue to glutamic acid 43 residue. You have a 1.7 Armstrong distance hydrogen bond. Okay, that's the meaning. Here, what you see, again, from over here, the direction comes here, and from what you see, cysteine. From cysteine 161 position to cysteine 40, we have a 2.3 Armstrong distance hydrogen bond. How about here? What is different? Normally you see here. Now direction from where to where? Serine 99 to histidine 92. Hydrogen bond. 1.9 Armstrong distance. The last one here. From serine 110 to what is G? Glycine 65. You have hydrogen bond, the distance 1.8 Armstrong. These are a bit complex, but they use a Fourier mapping control function. And if I'm not wrong, they use density functional theory here for these calculations. Okay, now it's finished. Is there another question? Okay, let's end here.
Is this technique according to monomer structure only?
This is just used for proteins.
Yes, but
They don't say
complex.
They don't say you can use it for any other complex. They just use it for proteins. So you don't know.